Okay, Bismillah ar-Rahman ar-Rahim. Salatu wassalamu ala ashrafil mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamu alaikum everyone. Today inshallah, still with control of manipulators and degree of freedom open serial chains. So and today inshallah we're going to be looking at, I guess this is something new completely for you. Have you ever heard about impedance control?
Yes. I
Okay.
heard about it, but not work.
Not work with it, okay. Who heard about impedance control before? In any context? On my lecture. Okay, good. So today, inshallah, will be a new topic, a new way of looking at control, and hopefully it will open a lot of doors. And so these last couple of, so this lecture and the next week's lectures, we're going to be opening, we're going to be posing more questions than answering them. Okay, just for time limitation. So it's up for you to investigate further. But this is impedance control is one of the bread and butter, techniques in manipulator control. Alaikum assalam wa barakatuh. And in my own research group, this is, we live on that stuff. Okay, and it's very helpful. So this is just a motivation in general. Let's start with a recap as usual. So last time we looked at, actually till the end of the semester, we're going to be looking at equations of this form, which, as you've seen, they characterize the equations of motion governing an n-link serial chain manipulator. So M, mass matrix, C, Coriolis and centripetal matrix, B is some friction, which can be nonlinear in general as a function of theta dot, and G are the gravity torques. And tau here, the one in red, is the control torques, the one that come from the actuators that we want to design a controller for. Okay? So our goal is to find tau equal something. Okay? So that's the goal. The state space form, okay, is how we're going to be starting with. Last time we looked at the open loop stability. And after we did the open loop stability, we looked at stabilization control. We said that our first objective is to make the manipulator go from one configuration to another. Okay? So we want to stabilize the system at a certain desired configuration. Stabilization means that you have a desired configuration, okay, for every link. And so for every joint that you have a desired angle, and the velocities are zero. So we don't want to do any tracking. The control law that we derived last time was the proportional and derivative term. We said that proportional is simply will be the gradient of some potential function that we design, and the derivative term is whatever will make the system stabilize itself. So, and this was the equation we came up with. Just to remind you, it was not enough just to assume that we have a spring, okay, that connected at every joint, which is in the end gives something like minus Kp multiplied by the error, which is like a spring force or a spring torque. We also needed to compensate for the gravity. And the name of this controller was simply PD plus gravity compensation. Okay, so PD plus gravity compensation was the controller we derived last time. And we've looked at the closed loop stability of that system, and we've seen that, okay, we have a global asymptotically equilibrium point, and last time I showed you a simulation, okay, we were able to reach from any configuration the configuration that we want. The control parameters here are Kp and Kd. Kp and Kd can be generic matrices. You can play around with it to have different performance as you wish. Okay. Any questions on this part before we move on? Yes, Asha.
Talking from the perspective of application.
Yeah.
This control, using this, we can go from one configuration to the other.
That's right.
We want to stay at that configuration.
Yeah.
From the practical point of view, do we still need to provide certain torque or certain voltage to the motors to keep it over there, or does it, because if there is no mechanism
Yeah.
to keep it over there, it will fall back under the influence of gravity?
Yeah.
So how do we ensure that it stays at that position?
That's a very good point. So let's see what happens to the control law. And the control law is equivalent to the motor torques that you provide, which is equivalent to the motor voltages eventually, after you take the motor dynamics into account. So what happens to them after we reach the equilibrium point? Okay, so we said that theta desired and zero are a global asymptotic equilibrium point, but when we go there, what's the control effort? Look at this control law and plug in the values that you want. So if I plug x1 equal to theta d, I get theta d minus theta d, 0. So the proportional term just canceled out. At least the spring force. There's no more. You don't need to apply any spring, okay, torque. The derivative term becomes 0. Okay, so you see here we have a 0. So after I reach there and I'm stabilizing, I don't need to apply any extra torque. What about the gravity here? Gravity at x1 equal theta desired, what happens to that?
There has to be some gravity compensation term.
It's a gravity compensation term, exactly. So since the tau will always be equal to this expression, the system will behave as if there is no gravity. And that's exactly what you've seen last time, right? So gravity is completely cancelled out. Okay? So you still, the motors will always need to be turned on to compensate for the gravity. Okay? If you apply some brakes, and that's something we didn't model here, okay? They're not modeled in the equation. You apply some brakes, then already you don't need to apply any torque because you just, you're clutching the mechanism.
So if we applied brakes, we should cancel the GX1?
No. This is how the system dynamically moves. The brakes is something else. Brakes is after you reach that, you just clutch it, and the dynamics, if you have brakes on, are all zero. You don't move. You don't, even this equation no longer is valid, right? If you're applying brakes, well, you're not going to be moving.
But if you are applying brakes and we still have certain gravity compensation torque coming from the motor, isn't it equivalent to applying brakes and still applying accelerator, and it will still cause some damage?
That's a static. That's another mechanical analysis point of view, not a dynamic analysis. In the dynamics point of view, stuff are moving, and you want to see how this system will evolve. Okay? Yes, Fahd.
Is that common? Like after when we reach a certain point for robot arm, do usually industrial robot arms have brakes that would stop it at this point, or is it something that only after when you turn off the arm?
The robot arm will keep on moving all the time. That's the thing, right?
Yeah.
So all the time you want to counteract the gravity because you're not going to be just going. Let's say that the problem is to go there and stay there. Of course, then it makes sense. Then you turn on the brakes.
Okay.
If you want it to stop, it's like you take your car, you go from somewhere, and then you apply P. You go to parking mode. So you don't need to keep on pressing. Okay, so that's the whole idea.
At the reaching point, you have to apply brakes, and then you unlock the brakes.
Exactly. It's no big deal, but we don't do it. We don't do it on off because that already has some issues on its own. Okay.
Okay, but I think answering this question, I think when you reach the position and you apply the brakes, there is no need to apply torques anymore. So I think the torque will be zero, and you only will need the brakes. So
That's the same idea as you take your car, you stand in a red light. Do you turn off your car to save petrol? You never do it. You could.
sometimes if there is a heavy traffic,
Okay. You wish, right? So maybe if you have a very fancy car, it will automatically turn off. So okay, if you can handle it, But you will not do it. You'll just keep on staying in that mode. And again, this is way beyond this is out of the reach of the controller. The controller is made to take you from one place to the other continuously, and to counteract the gravity as long as it's there. It doesn't have any brakes there.
I think most of the industrial robot arms, they are just pick and place. So I think you don't move all the joints.
So it's good that you brought that up, which is why we're going to be talking today about impedance control. So doing pick and place. So now let's generalize this, okay? And I'll break that what you just mentioned right now, that all robot armors are made for pick and place.
Most.
Okay, we'll see. So we're gonna really go now so pick and place lives in here. When you're using a robot arm to do pick and place, you're always thinking about motion control. Usually most of our control teaching, you start from state space stuff, or even before that, start from linear state space models, transfer functions, PID, root locus, all of that stuff. They come from the historically from electrical domain. So electrical systems, they started to have this idea of controlling voltages and blah 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 blah. When you go to the mechanical side, the first thing, as you've seen, that's the take-home message from this course, that we have a manifold, right? We don't no longer have just scalars going back and forth. We have a configuration space, so things are more complicated at a mathematical sense. But not only that, when you even go further from mechanical systems in general to robotics, by definition, what is the meaning of a robot? You all know that. What's the definition of the word robot, the Czech word?
Anything that has sensors and actuators.
Yeah, that's technically, but the Czech word, the first person that thought of, robot. Slave worker, exactly, yeah. So technically it was, robota, yeah, exactly, slave worker. So you made robots to what? To do what? to do jobs. And that jobs include what?
Interaction.
What kind of action?
Interaction.
With the environment.
Interaction with the environment, exactly. So by definition, we created robots to actually interact with the environment. And now I'll tell you, now let's compare, if you want to do motion control, how is it different from interaction control? Let's take them one point at a time. If you're starting with motion control, for example, let's say that you have a system like that, okay, you have a tracking satellite. It's mechanical still, okay? You want it to track something in the sky, okay, or to have some certain desired angle. The main objective in a motion controller is that you want to achieve stability, you want to be stable, you want to reject external disturbances, and you want to maximize performance. You all agree? Okay, typical requirements. If you want to do interaction control, the main objective would be to interact with an unknown environment, to be stable, and also to be safe. And safety is something different than stability, okay? So stability means that, I'm not gonna be, I'm gonna converge to some equilibrium point. But safety is something more. I'm not gonna kill the person next to me if it's a human. I'm not gonna break the environment. So it's something else. In motion control, you have a closed dynamical system. Do you see here any environment? Mathematically, there is an environment. For example, we usually consider the environment everything we don't model, right? For example, friction can be in the environment. Aerodynamics can be the environment. But usually, the environment itself, okay, I don't model it, and I consider it as disturbances. And I treat the system I want to control as a closed dynamical system. And when we want to do analysis, okay, when we did the Lyapunov analysis, we do stability analysis using a closed loop model. So it's a closed loop, which means that it's not interacting with the outside world. When you have an open dynamical system in interaction control, the unknown environment, you need to include it into the stability analysis. But by definition, it's unknown. So how can I put it into an analysis that I don't even know what the model looks like? Sorry? No, I'm talking about the environmental. When I say environment, think of the following scenario, okay? Think of a robot drawing, drawing on a circle that's unknown, drawing on a surface that's unknown. You don't know what the surface properties looks like. You don't know how big, how small, how smooth, how rough is it, and so on. So you don't know the environment. So if I'm doing analysis, I need to take that into account. It's unknown. Okay? In motion control, you're based on unilateral signals. You're all familiar with block diagrams, right? I have one signal going from one way to the other, and then after that I have a signal, and after that I have a signal, and so on. If you go back to this throughout the whole course, you'll find that I've been usually using signals usually together in a bilateral way. For example, torques and velocities and angular velocities, they're always going opposite each other, together. Twists and wrenches, forces and velocities. You always have two things, going back and forth. So there is a way of that you're actually not controlling simply the position or the velocity of the system. You actually are controlling the relation between these two back and forth variables. For example, in general, there will be something velocity-like and something force-like for a mechanical system, for a robotic system. So for interaction control, these are typical problems that you can see in interaction control. For example, this is usually it's a classical problem called the peg in a hole problem. Okay? It's an insertion. You have something that you want to insert it into a hole, and this hole can be big, can be small, depending on the clearance. It depends on the problem. Typical example, keys, key insertion. You do it all the time. You want to enter your room, you insert a key. Okay? Again, you can think of so many scenarios. This is just an abstraction. Here, for example, this is opening a valve. Okay, having some sort of crank shaft, crank behavior. Okay, you can have the sliding on the surface. You can have more stuff. Okay. In these cases, so imagine that this is the end effector of a robot arm. Controlling either the pose or the wrench means that you need to know exactly how the environment looks like, the task how it looks like. Okay. And when exactly the contact occur or not. Okay? And that's not possible. For example, if I have this, this piece, I want to insert it into the hole, I need to know exactly, okay, where is this in the environment? Okay, how big is it? How small is it? Even if I'm using sensors, for example, vision, and I'm doing back and so on and so forth, it will never be perfect. Which means that in the controller side, I cannot assume this is a perfect knowledge. Same also even for the mechanical properties here. If I'm rotating this shaft, this is the environment for me. I don't know what the friction is. So I cannot take it, I cannot cancel it, or I cannot compensate for it because it's unknown in general. So the first one actually to look into this problem from a different way is not to control position and forces, okay, or in general pose or wrench. You actually control the behavior between them, okay? And this is a completely different way of doing control. I'm not interested in designing something that regulates the force, stabilizes the system, okay, or tracks a certain trajectory. I'm interested in making the behavior of the robot seen at the end effector behave in a certain way, desired behavior. Okay? And that led to this impedance control. Okay? So this is a slide from last year. Okay? So Neville Hogan, okay, is an MIT professor, okay, and he has one of his seminal works was a 3-part paper. Okay? Long time ago, I think it was 1985. Yeah, 1985. It was on the topic of impedance control. He posed this question. Okay? I strongly recommend you read them, okay, if you're going to work in that area. Okay? So impedance control is well known in robotics. This was how it started. Okay? So, and this, by the way, these are citations from last year. Okay? So I forgot to update them. So you can check out. They definitely increase. So this has 7,000 citations. Okay? One of this paper. Okay? So it's, and everyone in robotics should know about them. Okay? Now, what's the idea of impedance? Who heard the term impedance before on its own? In what sense? Electrical circuits, right? So you all heard about, you should have heard about impedance from electrical circuits, and you also have heard about the opposite of impedance, which is it remember what's the name? No, not in resistance. Admittance, exactly. So Z here, we denote by it impedance, and Y we do not by it admittance. Just to remind you a little bit, let's go a little back to electrical impedance or electrical admittance. Okay, if you have an AC source, you have to have now an alternating current source. And you have here a bunch of resistors and capacitors and inductors. You can model all of that stuff. You can combine them, lump them together such that it has one equivalent impedance. Okay? And this equivalent impedance was simply the relation between, it would model the relation between voltage and current. And it was depending on the frequency. So we had to go to the frequency domain. We had to go to the complex domain. We had here a J here. So this was a complex domain. And this, we had an R and an X. Okay? So the R was the resistive value, the real part of this impedance, and X was the imaginary part. And it included the values of the inductance and the capacitance and also the frequency, okay, content. Admittance is simply the opposite of that. It's the relation between, so if you look at this equation, you see it is voltage is equal to Z multiplied by I, right? And in this equation, I is equal to voltage multiplied by Y. Okay, so it's like one has an input-output relation, and this has an output-input relation. It's just the opposite. Okay, one is so we have to look at causality. So here, current is an input, voltage is an output when we talk about impedance, and voltage is an input and current is an output when we talk about admittance. Okay, and just to remind you, when we talk about this, we have to do it as a phasor, so we need to look into phasors in the frequency domain. So this might ring a bell, but we don't need it. So I'm just reminding you, we're not going to do things here. I just want to do an analogy from electrical and admittance and impedance to mechanical admittance and impedance. Have you ever thought about that an RLC circuit actually behaves the same way as a mass spring damper circuit from a mathematical point of view, analytically? Write both differential equations, go back home, okay, ChatGPT it, tell it, write for me, for first order as a linear system, write the equations of motion as of a mass spring damper and the equation of motion of our RLC circuit. You'll find they're exactly the same. The only thing that changes is the numbers, the physical meaning there. You'll find that the mass is equivalent to the inductance, the resistance is equivalent to the damping, and the stiffness is equivalent to the capacitance, okay, related to it, okay, not directly, okay. And thus we can also define something called, in mechanical engineering, we can define something called mechanical impedance, which is simply the relation between force and velocity. So now instead of voltage and current, we have force and velocity. And admittance would be the reciprocal of that relation. So the relation between velocity and force. So here, velocity is an input, force is an output. Here, force is an input, velocity is an output. Make sense? Okay. Okay. Makes sense for everyone? Okay. So now this is the analogy between mechanical impedance and electrical impedance, just to put them side by side. So impedance, if you write it in as a transfer function in the S domain and the Laplace domain, you'll find it looks like that. Okay. MS squared plus BS plus K. So this is the mass spring damper system. We have motion as the input. Okay. We have something, the integral of the velocity, which is the motion, the position of the point mass there. So this is an input, and force is an output. While the opposite, if you're talking about admittance, then we have force as the input and admittance as the output. Okay. Now the whole idea of impedance control is the following. Okay. So that was the proposal of Neville Hogan. So he said that instead of commanding exact positions or forces, we can make the robot to be controlled to behave like a mechanical impedance. Okay? At the end effector, the one which is it's interacting with the environment, we can make it behave as a mass and spring and damper system. Yes, Fahd?
Going back, the idea of mechanical impedance and admittance, does that have any physical meaning? I've never seen this way of representing mechanical systems. Like, Z equals F over V. F over V is not something that we have actually looked at before. So does it have any meaning, physical meaning?
Yeah. Have you ever seen the transfer function of a mass spring damper system?
Yeah.
So you've seen it.
Okay. And admittance also, is it just the reciprocal and that's it?
Yeah. It's simply the relation, of course, in the frequency domain, which it depends, it's a generalization. This is only valid for linear systems. However, the idea you can generalize it to nonlinear systems. Okay. We cannot write it as a transfer function for nonlinear systems, but still the idea is valid. You have a relation, okay, between force and position, or force and velocity. One is input, one is the output, okay? And they're always the reciprocal of one another, okay? So the idea of impedance control is simply that when the end effector of the robot gets an interaction wrench, something pushes on it or pulls on it, okay, so there's something interacting with it, we design the controller such that the whole robot behaves as if there is a mass and spring and damper virtually at the end effector. Okay? So you see what the whole idea is, that we're shaping the robot's dynamic behavior. And by dynamic behavior, we're talking about the impedance behavior. And what's the impedance behavior? It consists of some stiffness, some damping, and some inertia. We're shaping them to match a specific interaction dynamics that we would like to have, depending on the task, of course. Okay? So we're no longer thinking about, you go to the problem and say, okay, I want to control the position to be exactly this and the force to be exactly that. No, you control the dynamic behavior between them.
For the joints or links or the end effector, what? This for what? For the links or the end
For all
effector?
the joints or for just the end effector?
So the control law for an N-link manipulator are all of the joint torques. We design them thinking about how the end effector will behave.
So we replace this system with the mass and the springer or what?
We'll do something similar to that. Yeah. We're going to shape the system so that it behaves as a mass and a spring and a damper. Yes, exactly. That's the whole idea. At the end effector. Okay. So that's the idea. But we'll formalize it, okay, today, inshallah. Okay. And also by next lecture. So we'll build this, okay, in a while.
Just like to make the working space, the workspace for the robot, like if this is a cube and this is the hole that we want to put the cube in. This is your workspace. You should not like pass like
Stop thinking. So don't overthink it. This is a completely new idea. Try to observe it as something, look at it with completely fresh eyes. Don't criticize it yet in your mind. Okay? So leave it, let it, sink until you see it, you implement it, and and then if you have something else, implement it. Compare it then. But at least, take the fresh idea, don't break it, along the way. So take it one step at a time, okay? Let's do the impedance control for a point mass, okay? First, okay, so let's assume our mechanical system is simply a point mass. And the point mass, we have a controller on it. So we have an interaction controller. It will apply to the point mass a force, and we're going to be measuring from this point mass the velocity of the robot, of the point mass. And the mass itself, okay, because now we're doing interaction, it can push on the wall. It can interact with an environment. So when it pushes on the wall, there will be a reaction force from the wall, Fint, and also it depends on the velocity. The environment will constrain the velocity, for example. It will prevent the velocity of the mass to be in certain directions. Okay? For example, after the mass comes here, the velocity is only constrained to go up and down, not to go back and forth. Okay? Not to go forward, but it can go backward. So you have some constraints there. So we're going to do everything Euclidean, so let's leave the geometric stuff later. So everything is in Rn, so the governing equations of motion of the point mass, no gravity also. Okay? The gravity, you know how to treat it, right? Just compensate it in any situation. If you have a drone, you compensate gravity by just, canceling the wrench that you get from it. If you have a robot arm, you see, just compensate for the torques. Okay? So it's always the case. Gravity is the easiest thing to treat. Okay? Now the governing equations of motion of a point mass are psi dot equal to v, so rate of change of position is equal to velocity, and this is mv dot, is the rate of change of the momentum equal to applied force. I have a force from the controller and a force from the interaction with the environment. So impedance controller, simply, we want the system to behave. In other words, we want the environment to see our whole system, and by whole system I mean the point mass, the physical point mass, but also the controller, okay, which will act as if it's some virtual physical system, to behave as if it's a mass spring damper system. Does that make sense? Where Q here will be psi minus psi desired. Okay, so the location where I want to go, okay, is psi desired, and psi is the actual point mass. Okay, so the difference between them. So you see here, eventually, okay, this is the equation of a mass spring damper system. Okay, what is the input and the output here? The input are the Q's. Okay, so the motion, the relative distance between where I am and where I want to go, and the output is the interaction wrench. Okay, so this is the behavior that we want to control. If this is the desired task space dynamics, then you can easily check, just very easy, just playing around with linear equations, that the controller has to be given by that expression. Okay. So I ask you to compare. So what I want you to do is that take this expression, plug it in here, use the definition of Q, and see whether you get this expression or not. You can eyeball it in a minute. Take just 1 minute to look at it. If it takes longer, you can do it at home at your own pace.
This K and B, it is PD control.
What do you mean by PD control? We never talk about PD control. K and B, you can think of it as gains of the impedance controller. Yes.
And this M zeta double dot, it could be the F interaction?
No. The M, so psi double dot. So psi desired is where we want to go. Psi desired dot is the rate of change of that trajectory. Psi double dot is psi desired double dot is the second derivative.
You mentioned that we need to compare this with the above one.
No, take this, plug it in here.
In the F controls. Right?
Yes.
So K and B, the gains for the BD control.
For the impedance control.
For F control.
F control, this is an impedance controller.
K and B.
Yeah, K and B are the gains of the impedance controller.
So it will be F int, it will be M zeta double dot, right?
So F int, no. F int will be equal to that expression. After you plug that in. Let's do it quickly. This is Q.
Okay.
This is Q dot. And after I plug this in there, I get M psi double dot minus M psi desired double dot, which is MQ double dot. So I'm left with that term. And here there was minuses. When I put them on that side, they become a plus like that. You just get a mass and a spring and a damper.
So it always takes this one.
For the point mass. No, for the point mass. The idea is very general. No, you have no idea. Okay? But at least for the point mass, this is how it looks like. And we'll come to that in the next slide.
The idea, I think it is similar to the feedback linearization. Here we take the k error and k error dot and feed forward the zeta double dot.
But we do this with the non-linear part of the equation. But here, where is the non-linear part?
Yeah, you have to wait. You have to wait till we go to the nonlinear system and see how it looks like.
If we say, for example, the highest order for the system, it is, for example, v, or if con, it will be all this control.
Okay.
So it is similar to what we do in the feedback linearization.
This is the point mass example. So it's a very trivial case. So actually, you cannot. It's very hard to say it. You know, how does it look like? In order to do that, to be fair, you need to start with something very complicated, and do the steps and see what you get in the end, and then you can say what it looks like. What actually makes sense, okay, which is something some of you said it that actually. Wait a second. Yeah, okay. Now, before I tell you what does this look like, let's see what happens when we use this controller for interaction. Now, this is the new part. Okay? This is the new way of looking at what happens with this controller. This is now the controller implemented. When we go for interaction, what happens is the following. Okay? You see, this is before the interaction. The point mass is away from the wall. Okay? And then after I go to the wall, there will be a little bit of penetration. It's at the micro scale, the two surfaces, they penetrate each other. Even how, by definition, we say they are rigid bodies, right? But this rigid body assumption is not valid in real life. There's nothing rigid, okay? Even this table is not rigid, okay? The fact that actually I feel something when I press on it is because there is a penetration that happened between my skin and that table, okay? And so on, okay? So usually we have a very small penetration. And if the desired value is now inside, and this is where the psi is, you see I have a Q now, but Q dot and Q double dot are equal to, in this scenario, in this exact situation, Q dot and Q double dot are 0. I'm not moving, okay? So I took, the controller, I told the robot, okay? I told them point mass. If this is the wall, I told it come here. This is my desired point. But the wall is there. So actually it stopped here. And now what's going on? The point mass is doing what on the wall? It's pushing on the wall. What is the wall doing? It's pushing back, Newton's third law. So now, what is this force that the wall is pushing with? It has to compensate with the...
Should be the same as F interaction.
No, but what is F interaction? That's the point. It has to be equal K multiplied by psi minus psi desired. Psi desired is inside the wall, yes.
Did we move psi desired to be inside the environment?
Very easy. This is the desired point, right? You tell the robot where to go. For example, you have a robot arm, so I'm the robot. You tell me, go here, and then afterwards go down, down, down. This is your desired. Go down, down, down until here. And then I come to that point, what happens? You tell me go down, what do I do? I push further. I push more. Do I move?
No.
That's exactly what this equation says. I'm not moving anymore. However, the more you take psi desired inside of the wall, or vice versa, if you change the K itself, if you make it higher, you start to get more force applied on the environment. And that's the basic of something called active stiffness control. I'm actually changing the stiffness of the system such that it's pushing more on the environment. If you are moving now on the surface, for example, let's say that I want to push on the wall, but I also want to go back and forth. I want to draw something. I want to clean the surface. I assume, for example, this is a wall, and I want to clean that wall or paint that wall. So I want to push, but also go back and forth with some behavior. You can also look at how the B changes. So you can look at here, during the interaction, during the task, how this model changes. In any case, you will always have a behavior between F and the Q to be a mass spring damper system, because we designed it to be that. Okay. Now, the good question is, how does this change from PD control? Okay, what's the difference between that and PD control? The first time Neville Hogan, published this paper, 1985, immediately, I think a year or two afterwards, some people published and say, you know what, impedance control is rubbish. It's just PD control in disguise, and they have a point. Makes sense, right? Take a look at the two control laws. If we design the PD controller for F, okay, what's the difference now? M psi double dot desired, and the negative psi dot. You know what? How can we make this controller into that controller? Simply by doing tracking. This was a stabilization controller, so PD was for stabilization. If I want to do tracking, I'll get the same control law. Yeah, so it will be PD, but a tracking PD controller. Tracking a trajectory, yeah. And psi desired, this will be the feed forward term, and this will be the velocity of the desired trajectory. So in the end, there is nothing there, right? So immediately you might have, so if you were there back 1984 and you were not critical, you thought, you know what, this is not new and this is very bad. Let's say you were a reviewer of that paper. At that time you said, okay, this is a very bad idea. You killed it and that's it. And frankly, alhamdulillah, Neville Hogan never gave up, okay? He kept on pushing for the idea. Because he was not talking about the control law, and this is the main message I want to get out of here today. It doesn't matter what the control law looks like. It matters how you reach that control law. What is the idea behind how you design the controller? And that's exactly, we've actually seen that before throughout the course. You remember when we talked about PD control and energy balancing control? When we started with PD control, what did we start with? An error in position, an error in velocity, multiplied this by the Kp, multiplied this by the Kg, and then you get a controller. But was that way of thinking enough for us to go to geometric control on SO3? No, we did not do that. We thought of, you know what, the proportional term comes from the gradient of some potential function, and this comes from whatever will make the system stable. So I can generalize this idea to SO3. And that's the same idea. The way of thinking about impedance control, so the whole idea of PD control versus impedance control is the approach, not just the control law. In PD control, you want to track a desired position, and you don't think about interaction. While here, you want to shape the dynamic interaction, so you're thinking about the interaction from the start. Okay? So that's the first thing. The second thing is that external disturbances, if you have them when you're doing PD control, you think of them as disturbances. And if you have something that prevents you from reaching the desired location, what do you do in a PD controller? What's the next step? Reject the disturbance. With what? What removes the steady state error? The integral term, exactly. So I need to add an integral term here. Do I need to add an integrator here to remove the interaction wrench, the interaction force? We actually need the interaction wrench. So actually putting an integrator here will defy the whole purpose of the control. So if the environment pushes on a PD controller, the robot will try to go as hard as possible, okay, very aggressively, because it's designed so that it tracks the trajectory very fast. While here, the robot, you can design it to comply as you wish. Okay? I can make the robot, if I push on it, I don't need it to push back. I need it just to go with me. And then when I remove my hand, it would go back. So compliance here, okay, is the key word. And the output behavior is that unless you manually tune the gains, okay, you're going to get a very stiff behavior because this is what you want to do. But here you can play around with the compliance through this virtual mass and spring and damper that we added. Okay.
Can we get the interaction control from the PD as well?
As an approach, okay, if you look at the control law, no way. Sorry, if you look at the control law, they are the same. They are exactly the same. Okay? But if you look about the approach, they are completely separate. The way you proceed in a PD controller is say, okay, I have an error and I want to integrate, that error and to do a rejection of the disturbances and so on and so forth.
My point is, if I think that I want to design a PD controller for interaction, can I still get to that point using a PD controller?
Do it. Okay, do it. Okay, again, so it's like, can you do it? Think about it. But now the thing is that this is in retrospective, which means that he already came up with the idea, 30 years ago? 30 years ago. He already came up with the idea. Actually, 40 years ago. So he came up with the idea, and then it had all of the citations I showed you. So It's not that trivial. It's not that, no, that it was actually PD in disguise. It's completely separate.
So correct me if I'm wrong, yani. Here in the impedance control, we deal with we use it for interaction purpose, and we deal for any object to interact with as mass Springer system. So
No,
for
no,
table,
no,
spring,
no, that's not true. I'm not saying that the environment is in a mass spring and damper system. What I'm saying that the closed loop system at the end effector, you want it to behave as a mass and spring and damper system.
closed loop for the system, for the arm.
For the arm and the controller together. You see, there is no, so there are two things here. There is a physical environment, physical wall, physical point mass, and a virtual spring and a virtual damper.
So we convert all the robot to this mass Springer.
We haven't talked about the robot yet, which is the next section. Okay, but here, if this is a point mass, the spring and the damper, they are the behavior of the controller. So now the controller is you no longer think of the controller as a proportional term and a derivative term. The proportional actually is emulating, is replicating a virtual spring and a damper. When you combine that virtual spring and a damper with your mass, you get a mass spring damper of the whole closed loop system.
But what is the relation of this spring for the system with the environment? And this spring, the stiffness or the damping, it usually uses for to know the position for this mass wear or the velocity.
No,
the
no,
velocity.
no. Now the spring and the damper are the controller. This is psi desired, this is psi actual. Imagine the following. Imagine this was a real system. Imagine that. So this is the end point of the spring, and this is another end. You imagine that? I'm going to take this end and bring it here. What happens to this side, to the mass?
In the 3D environment, in the 3D?
Yeah, in 2D, in the plane. I took the spring and a damper and I pushed them like this. In 3D, whatever. Yeah, okay. Think of it that, okay, I took it behind the board. Okay. Okay. So now the spring and the damper are here, and the point mass is here. And I'm pulling more, side to side. What happens to the mass? Pulled until it hits what?
The environment.
You get something like this.
Okay.
So you see side desired is here now. And the mass is here. And I'm pulling more. What's the mass doing? Pushing on the wall. So you see, this thing is actually virtual. Virtual physics. This is the real physics.
I apologize, but how the spring it will be flipped inside the wall?
It's virtual.
How the relation or the intuition look?
This is the intuition. Very easy. Okay, so I'll say it in another way. This is the point mass. And there's a spring and a damper here, virtual. And this is the side desired. Okay? You agree?
Okay.
So if I want psi equal side desired to be, if I want psi to be equal side desired, and this is the spring and damper, what will happen now? This will come here, right?
Okay.
You agree?
Okay.
So the spring and the damper, what happens to them?
Compressed?
Compressed, exactly, up until zero, right? As if they disappear. You agree?
Okay.
So I go down. What happens to the mass?
It will be relaxed and compressed again.
Right? What happens now?
Okay.
What happens now?
Compressed and relaxed again.
And if I push now further, what happens? What happens now?
Okay. Till?
It will push back.
Oh, okay. So
Now
here
we
till
can
till reach the environment.
Yes?
Okay. Oh.
Wouldn't that make it push harder?
So here it is like
Yeah,
end.
it will push harder on the wall.
But if it's
It looks like to end with two masses, right?
No. This is the end point of the spring and the damper, and it's connected to something that's virtual. It's the end point. You can move the end point around.
in the normal BD controller, if you have a robot arm and someone put the position,
Forget about the robot arm yet.
position, to be behind the wall,
Okay?
the robot arm would just try to push
That's right.
until it may break. But what in the impedance control?
No, you're saying in a PD controller.
Yeah.
If this is the PD controller, If this is
I'm comparing between PD controller and
of a robot arm,
yeah.
we haven't got that yet, so we'll keep that question. Next lecture.
A point mass.
Okay, point mass.
Point mass.
Okay.
It will,
So you're talking about these two controllers.
yeah, in the PD controller, it will just try to push the wall.
That's right.
Okay. Until it may break.
That's right. Yeah, absolutely.
In the impedance control,
The same.
How can it know that it has no use to push?
K, choose K here to be K here, B here to be here, you get the same performance. Exactly.
So in the impedance control, it will just push the wall as hard as it can.
If the same if the same gains you have them here and there, so it'll be exactly the same controller.
What is the difference between them?
You don't see it. That's the thing. In this situation I'm talking about, in this scenario, this is a trivial example. You know, when you go a very trivial example, the difference is they start to become vague. What I want to point out is how did we reach that controller? How did we reach that controller? So the way you start here and the way you augment it. So here, not reaching, if psi doesn't reach psi desired in a PD controller, is that something good or bad? Something very bad. The controller has failed. But here, psi desired actually is no longer called the desired set point. It's called usually a virtual set point that I'm going to be moving around. I know I don't want to go there. I'm just going to be moving the system around with it to interact with the environment, but not to actually go there and to stay there and to reject any disturbances after I reach.
But the point mass will still try to push the environment.
That's okay. That's okay. If it's within the mechanical limits, nothing will break. I increase the stiffness, I push more. And that's what you want, right? You want to interact with the environment. You want to apply forces. So objective met.
Okay, but interact with in a good way, but not in a bad way.
What's a good way? You haven't decided it yet.
From the overall summary of it, it seems that impedance control is more general than PD control, in the sense that my question actually would be, we have been using PD control mainly for either tracking or stabilization.
That's right.
For the impedance control, we can do it for the interaction with the environment.
We're doing it for the interaction. Yes.
Can we implement impedance control to achieve the objective of PD control?
It's already doing that.
Yeah.
That's exactly what I mentioned here. When I don't have any interaction, the impedance controller is nothing else than a PD controller. It's just a tracking controller.
So it's more general than the PD control.
It's a completely different framework. And to see that, we have to go to something more complicated. To really start seeing the difference in the point mass, okay, things start to get a little bit vague because it's already a very trivial example. We don't have any, we don't have real, we don't have nonlinear dynamics. We don't have a complicated system, so it's very hard to see it. Let's go through the robot arm and see what happens. Okay, we're not going to be able to finish that today, so that's why we're going to be starting first by looking at what is the dynamics of the robot when you look at it from the end effector, something called the task space dynamics. Okay. So now, just a recap. So this is the equations of motion, but now the robot is interacting at the end effector. And by the way, there is nothing that prevents the robot to actually interact at any point throughout its body. But let's keep it at the end effector for simplicity. Okay. So I have an end effector frame, E, at the tip of the robot, and I wanted to push or pull or do something at the environment. So we have a controller torque and we have an interaction torque. Now, first thing that I want to remind you of, that what is the equation that relates the interaction torque, okay, to the actual forces and torques that are happening at the environment? You have the Jacobian, the geometric Jacobian. So the geometric Jacobian was the relation that goes from theta dot to the end effector twist, the twist of the end effector with respect to the base of the robot expressed in the end effector frame, the body twist of the end effector, and vice versa. Okay, we have the transpose, the dual relation between the end effector wrench, so torques and forces at the end effector, between the environment and the tip of the robot, okay, mapped to the interaction torques. Okay, so I have here J on one side and J transpose on the other side. Does that ring a bell? Or did we leave it too long that you forgot? Hope not, okay? So this is again the geometric Jacobian. So J, okay, is the map from theta dot to the end effector twist. and the J transpose is the dual of that map. So what the Jacobian does is simply it will give us an instantaneous kinematic relation between the joint space and the task space. So these two things, so these two variables, so this velocity-like variable and this force-like variable, they belong to the joint space. You all agree? They are the joints of the robot. So angular velocities of the robot joints, and these are the torques applied at the robot joints. You all agree? And in this side, we have the motion, the generalized velocity of the end effector in space, and the interaction wrench also in space. Both of them expressed in the same frame, and in this case, it's the end effector frame. Okay? So in this side, usually this is called the task space side, and this is usually called the joint space side. The dynamics that we had earlier are represented in the task space or in the joint space. These are expressed in the joint space or in the task space. Joint space. They are all, as you see, it's a differential equation in terms of theta, theta dot, theta double dot, and the torques. So it's all in the joint spaces. It describes how the joint dynamics looks like. And just to remind you, okay, this is just a reminder that each column here of the J was simply, was a screw axis transformed, blah, 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 blah. You can go back at your own pace to review that. And we have that the transpose of it is the relation between the wrench and the torques. The Jacobian, I mentioned before, it's very important for so many things. One of the key things that's very important is that it identifies something called the kinematic singularities of the robot. Are you familiar with this term, singularities of the robot? So something to look at. We did not cover it, okay, but it's something to look at. Okay.
The end effector, when it reaches something, it cannot rotate, cannot reach the same point.
It's simply from a mathematical point of view. It is actually you will not see it here, okay, but I'll mention it in a couple of slides. Okay, but you don't see it here. Why there is something called a singularity? Okay, but until we reach that point, I'll mention it. Okay, but just know that kinematic singularities are related to the Jacobian, more precisely the Jacobian transpose. Okay, this is again a reminder. When we had the two-link robot arm that we did in the tutorial, and if you go back to the MATLAB tutorials, we actually derived the Jacobian to be something like this. So we had 0, 0, and 1, 0, 0, and 1, which because they were screw axes, and here these were the rotational parts. So they were the translational parts of the screw axis, and they had something like this. Okay, and J and J1 and J2 were just scalar functions. Okay, so in general, the bottom line is that the Jacobian is a function of theta, function of theta 1 and theta 2. Now, what we want to do is the following, okay? And remember why we're doing that. We want to do impedance control, but that's not lecture, okay? So next Sunday, inshallah. So, but for now, I want you to think about that question. If this is the dynamics of the system in the joint space, what happens, or how can we represent the dynamics, the same dynamics of the robot, seen from the task space? Okay? So that later on, when we want that the task space behaves in a certain way, we know already how does it behave. What is the actual behavior of it? Okay? And to actually write it is it's not that hard, and that's actually left as a homework for you. Okay? The equation is the procedure is very simple. You see what we have here on this side? J transpose, right? Let's multiply both sides by. If you multiply by J, what happens?
They will cancel.
Is J the inverse of J transpose?
No.
Is J the inverse of J transpose so that they cancel out? No. What is the inverse of J transpose? J transpose inverse. Okay. So I multiply both sides by the inverse of this matrix, which is J inverse transpose. So this drops out. So I'm going to be left here with a wrench equation, so a wrench variable. And on this side, I'm going to have J inverse transpose, J inverse transpose, J inverse transpose, J inverse transpose. Make sense? Okay. But also what I can do is that the theta dot itself, if you go back to this equation, the theta dot, I can also write it as, I can replace theta dot by J inverse multiplied by the twist. And if I want to have J double dot, I would differentiate that equation. So I'm going to have V dot will appear multiplied by J plus V multiplied by J dot, or sorry, J inverse dot. Okay? You agree? This is, you're going to have it in the homework, okay? But eventually, you're going to find that I can rewrite the whole equation into something that looks like this. Okay? Something multiplied by V dot, the twist dot, plus something multiplied by V, plus something that corresponds to, okay, the gravity torques, and in the end, I'm going to have the wrench interaction at the end effector as it is. This is an equation. So if this was an n by n, if this was an n dimensional equation, it was n equations, right, simultaneous ordinary differential equations together, nonlinear. This will be a 6-dimensional one because it's only, I have 6 components of the wrench, 6 components of the twist. So this will have to be a 6 by 6 matrix. This will have to be a 6 by 6 matrix, and this will have to be a 6 by 1 covector. Okay. So what we did is simply that we took the joint space dynamics. We multiplied, we took the effect of the J and the J transpose, but as an inverse, and we combined both of these together to have now an input-output relation between. So I have an input equation here, which is the V. Sorry, I have an input, which is the V, the twist, and the output, which is the wrench. Okay? Which is exactly the same here. If you go back, it was equivalent that I have an equation here as a function of theta dot. Okay? And here I have an equation that gives me the torque in the end. Yes.
We keep switching between the small c and b.
Yes.
And the capital.
Yeah.
What's the difference?
If you remember last time we said that capital C multiplied by theta dot is the small c, and capital B multiplied by theta dot is also the small b. We just write them like that. Okay. So now we're left with this new equation of motion that corresponds to the task. This is called the task space dynamics. Okay. So it's as the end effector, what does the environment see? Okay. So at the end effector, if I push at the end effector now, so you see if there's something that pushes at the end effector, the whole robot will behave as if this is an inertia called an apparent inertia, and it will have some nonlinear friction there, okay, that depends on theta and V, and it will have an apparent gravitational wrench. You see, everything is called apparent. Why? Because if I'm pushing at the end effector, okay, for every configuration, of course, you see this is configuration dependent, depends on the theta. Every configuration, the inertia and the friction and the gravity will change. Okay? But still, I'm going to feel something at the end effector. Now, what we're going to be doing next time is simply, we don't want the system to behave like this. This is the real system, the real dynamics at C as seen from the end effector. What we want is that we want this to behave as if it's an impedance control. We want to replace all of this behavior as if it's a mass and spring and damper system, another impedance, but we design it. So this is the actual impedance of the system. And you see, what does this remind you of? Just to stop it for a bit. What does this equation remind you of? If I remove this term, the gravity term, have you seen something that relates the wrench and the twist dot before? Without the gravity. Have you seen something like this before? The Euler-Poincaré equation. The Euler-Poincaré equation, what was it? Does anyone remember? I V dot, right? And then you had here a term which should have been minus add transpose as a function of V, multiplied by V. There was an I also there, multiplied by V. And then we did not never talk about gravity there, but if we actually had gravity, it would depend on where we are, so we would have some configuration dependence. And then we had the wrench that's applied on this Euler-Poincaré equation, the external wrenches. This is here it is the interaction one. Okay. And by the way, we removed the controller. Just to remind you here, I removed the control torques. So this is if you go to the robot arm, so you take the Francas that we have down there. Okay, you turn off the brakes, you turn off the motors, and you just push at the end effector. You're going to feel as if there is inertia given by this expression and friction given by that expression. And of course, there will be gravity given by that expression. Okay? So this is the apparent stuff. And of course, I put here, okay, there's just a technical remark that you can only actually push the robot arm at the end effector, and it will move if you have something called back-drivable robots. Okay, so back-drivable robots have specific, motors that are used, and they're usually more expensive. Okay, of course, and the brakes are not activated and blah blah blah. Okay, so you cannot do that for any robot. Okay, just practically speaking. Any questions? Okay, make sense? Want to stop? Okay, let's stop here. Okay, so next time, inshallah, we're going to be continuing with this, and I'm going to show you now how do we design the impedance controller for that system now. Okay, jazakumullah khair.